Welcome to Brain Vision.
Okay, we're going to start this question by drawing the free body diagram. We're going to start by the conveyor belt, which we have right here. We have point A on the left, point B up here on the right. We know the whole base of the conveyor belt is 8 meters, and so it's going to be 4 meters on each half. And right in the middle, where the center of mass is going to be called point G. We also know that the conveyor is at an angle of 30 degrees to the horizontal. Now, the velocities that we have acting on the system, we have VA, which is acting down on point A, which is the sand being dropped onto the conveyor belt. And then we have VB, which is up here acting at an angle, which is the speed of the conveyor belt. And now for forces acting on the system, we have FG right here, which is the gravitational force of the entire sand acting on the system right at the center of mass. And what the question is asking us to solve is for the vertical and horizontal forces at point A and point B. So point A, because the velocity is only acting in vertical manner, we are only going to have a vertical force. So we have that right here going up, and we will call that a Y. At point B, we have the velocity acting at an angle, so we're going to have both a vertical, By, and a horizontal force, Bx. So those are the three forces that we're going to be solving for. All the givens are stated clearly in the question, so we're going to start by going through. First, we are going to solve for AY, the vertical force at point A, and we're going to do this by using the steady flow equation so that we know the sum of the momentum at point B is equal to the mass rate, dm dt, times the difference of the momentums from point B and point A, which is, and momentum is equal to the distance times the velocity. So we have those for A and B right here. So this up. So starting with the left half equation, trying to find the sum of the momentum at point B. We have two forces acting on the system, the gravity and the horizontal or the vertical force at point A, which is AY. So we're going to have F of G acting at a distance of RG. And then we're also going to have, so that is acting one way, and the opposite way is AY acting at a distance of RA. And so we know FG from the givens, which is the weight of the sand, which is 750 kilograms, times the gravitational acceleration, which is 9.81, times RG, which is the vertical distance between B and G, which is 4 meters. And then we are subtracting AY, which we do not know, times RA, which is the distance from A to B, which is 8 meters. So that's the left half of the equation. So once you simplify that, you have sum of MB is equal to 29,430 minus 8 times AY. Now the right half of the equation is the dm dt times the difference of momentums. So we know that dm dt times the difference of momentums, which is RB VB minus RA VA. We know the mass rate is 50 kilograms per second. And we know RB, the radius from point B to B, is 0. So the first half of that set is 0, minus RA, which is 8, times VA, which is 10. So once you simplify it down, you're going to get 50 times negative 80, which is equal to negative 4,000. So then you set both halves of those equations equal to each other. So you're going to get 29,430 minus 8 AY is equal to negative 4,000. So now you only have one variable left in the equation, which is AY. You do algebra, you solve, and you get AY is equal to 4,178.8 newtons, or 4.18 kilonewtons. So we have that as a solution for the vertical force at point A. Like we said before, there is no horizontal force, so now we can move on to point B, to the forces at point B. We're going to start by finding Bx, the horizontal force. So we do this by we know the sum of the horizontal forces is equal to the mass rate, dm dt, times the difference of the horizontal velocities, which is v bx minus v a x. And so the only horizontal forces acting on the system are bx. So we know that that side of the equation is equal to bx, and that's the only force. So now we have dm dt, which is equal to 50 kilograms per second. And we have vbx, which is the speed of the conveyor belt, 1.5, and we want the horizontal component, so we're going to do the cosine of 30 degrees. And vax, like we stated before, there is no horizontal velocity at point A, so that is 0. So now we just have bx equals 50 times 1.5 times the cosine of 30. Fix that. So now we know bx, once you plug and chug, is equal to 64.5 newtons. So now we have ay and bx. The last thing we have to solve for is by. So we use the same equation we just used except for the vertical forces. So we have the sum of all vertical forces is going to be equal to dm dt times the difference of the vertical velocities, which is v by minus v a y. So we know the sum of Fy. Now we have multiple vertical force acting system. We have Ay, we have Fg, and we have By. So we know that the sum of Fy is equal to By plus Ay minus Fg. And so we do not know By, but we know the other two. So we know that this is equal to By plus 4180 newtons from the first part of this problem, minus 750, which is the mass of the system, times the gravitational acceleration, 9.81. So that is the left side of the equation. On the right side of the equation, we have the mass rate, dm dt, is times the vertical velocity at point B minus the vertical velocity at point A. So now we know that is 50 kilograms per second times the 1.5 speed of the conveyor belt. Now we want the vertical component, so we're going to do sine of 30 degrees minus the negative 10, since the velocity at point A is acting down. So we know that. So now we know both sides of the equation. So now it's just setting them equal to each other. So we have by let's see, set that back. By plus 4180 newtons minus this 7357.5 newtons from the gravitational force is equal to 537.5, which is that 50 times 1.5 sine of 30 minus a negative 10. So now we have all the numbers, and it's just solving for by at this point. So once you plug and chug all that, you get by is equal to 3.7 2 kilonewtons. And now you have all the vertical and horizontal forces at point A and point B.